All right, so one more structure that we're going to analyze the conformation of it. So butane. First off, I want you to take your time, so pause the video, draw as many staggered and eclipse conformation of butane as much as you can. Okay, as much as you can. So you're going to look through carbon 3 and 2. And you're going to rotate whatever, so get staggered and eclipse. All right, and then check with me to draw the a Newman projection. If you can make the 2D structure or bond line structure to 3D, it's going to help a lot. Okay, so we have hydrogen point towards you, point away from you, point towards you, point away from you. All right, now that's the bond line structure. Look at the molecule from the side. The Newman projection will look through bond right here, 3 to 2. Okay, in this case. All right, so what you're going to see, this methyl group, the 2 hydrogen going to be right in front of you. All right, the methyl group going to point up. I'll take a look. So this is carbon 3, the dot right there. This methyl group right here will point up. We have, and these 2 hydrogen atoms will point down left and right. All right, so the wedge line, that's the left, the dashed line, that's to the right. All right. Now look through bond. Carbon 2 will be at the back of carbon 3. So I'm going to use the big circle to represent carbon 2. The methyl group point down. So you're going to see that this methyl group right below carbon 3. So that right below carbon 3. So methyl group, I'm going to put right there. That's a red methyl group there. All right. And the 2 hydrogen going to be point to the top, to the left side, to the left and to the right. Right. The wedge line to the left, dash line to the right. Then they both point up. Got that? That is a staggered conformation of butane. Just one of them though. There are multiple. Okay. All right. I'm going to name this conformation A, and then I'm going to rotate 60 degrees to the right, clockwise. All right. So the red methyl group here, I'm going to rotate the back carbon. Okay. The red methyl group will line up perfectly with the hydrogen right here. We got an eclipse conformation B, which is less stable, and you know that. Another 60 degrees. So go back to the staggered, but it's not staggered like the one in A. You know that? When these 2 methyl groups get closer, they have a little interaction. They have a little repulsion called steric interaction, costs about 3.8 kilojoule per mole. Right? So steric interaction is a repulsion when electron cloud from 2 different atoms or molecules are in proximity. I get closer. They just repel. Okay, and so less stable than the conformation where these 2 methyl groups are far apart, but it's still more stable than the eclipse. Okay, all right, another 60 degrees. Now this one is bad. 2 methyl group get really close, right? They line up. So we got torsional strain, got steric strain, cost 11 kilojoule per mole. Don't memorize this number. I don't care if you know it or not. All right, but I just want to show this is not that stable. All right. Another 60 degrees. This methyl group go to the right, go back. It looks just like the conformation C, but it's on the other side. All right. Another 60 degree, go back to conformation F, which is just like conformation B, but kind of flip on the other side, and go back down to conformation A. All right. Let's see. There are 6 conformation totals. All right. Now in A, hold on. All right, conformation A right here. So I'm going to call it an anti-staggered conformation. Now you call anti-staggered conformation. So the 2 methyl groups are far apart. Go to conformation B. That's an eclipse conformation. Right. Now C also a staggered, but it's less stable than the anti-staggered. This staggered is called gauge conformation. I think it's French, German, whatever, French. I think it's French. Right. So gauge less stable because 2 methyl groups get closer. Yeah, steric strain there, steric interaction. And another 60 degrees. This methyl group will line up perfectly right here. This is the poopiest eclipse. It's the most stable eclipse. I don't know what to call it. I just call it total eclipse. It totally eclipsed there. Okay, so a total eclipse conformation. And another 60 degrees, go back to gauge, right? The C and E, same thing, but on a different side. And another 60 degrees, the red methyl group go down to this hydrogen. You get an F, which is just like B, but flipped on the other side. Another 60 degrees, go back to A. Okay? All right, eclipse. Now, let's look at the energy diagram. Okay, this is an energy diagram. Let's see what happened there. The most stable conformation, of course, is the anti-staggered conformation at the bottom. That's your reference point. Okay, and now go to the Gauss conformation above. These two methyl group Gauss getting closer, got a cost about 3.8 kilojoule per mole, so less stable than the anti-conformation, but still more stable than the eclipse. Okay, so this is Gauss conformation, and we also have the eclipse conformation where methyl and hydrogen line up. Methyl hydrogen line up. All right. So the methyl and hydrogen pair is called 6 kilojoule per mole. Hydrogen pair 4 kilojoule per mole. So 4, 6, and 6, 16 kilojoule total relative to the energy level of the anti. Okay. And lastly, we have the previous eclipse, total eclipse at the top right here, the least stable. They got methyl torsional and steric strain and hydrogen pair, right? So 6 kilo, oh right here. So this is cost 4 kilojoule per mole each. Methyl cost 11 kilojoule per mole. The total is 19 kilojoule per mole up top right there, the least stable. Okay. All right, that's it. All right, that's for conformation of alkane. All right. Now let's go to the next video. We will practice a little bit more about Newman projection.